I work at IQM as the head of the quantum machine learning group. So this is my team here. And today I'm actually going to talk mostly about another company. So I'm going to talk about what does quantum supremacy mean. And I'm really going to focus on Google's 2019 experiment when discussing this. And then I'm going to talk a little bit about how their experiment could potentially be used in an application before finally just introducing a couple of the ideas that we're thinking about at IQM. So let's get started. So what is quantum supremacy? Well, this is a term that Prescott introduced kind of back in 2011 in a talk about quantum computing and its future. And he essentially said it's doing some task with a quantum computer that cannot be done with a normal digital computer. And I've kind of broken down how can you achieve quantum supremacy into kind of three things you need to do. So you need to choose a task that is difficult for classical computers. You actually need to do the task on a quantum computer. But also you kind of need to show everyone that you've done that task. So we're going to use this kind of structure a couple of times in the presentation. But notice that there's no mention of kind of usefulness, right? This is more of an academic definition, which I don't say is a bad thing, but it's more about showing you can do something with a quantum computer rather than you can do something useful. So let's talk about choosing a task difficult for classical computers. And there's always an element of belief in this. And that's because we're basing this on complexity theory, which at its very fundamental has a massive open question, which is, does P equal NP? So are the problems that you can solve equal to the problems that you can verify in polynomial time? And the question that we're kind of interested in when we're talking about supremacy is, are the problems you can solve in polynomial time with a quantum computer fundamentally different to the ones you can solve with a classical computer? So let's take probably the best known quantum algorithm, Shor's algorithm, which, amongst other things, can be used to factorize the product of two prime numbers. And this is a problem that we're kind of believing is in NP, so it's not classically efficient to solve, but is in BQP, i.e. with a quantum computer, we can do this in polynomial time. And this we know with Shor's algorithm. But we don't know if there's a classical efficient algorithm out there. It's just that lots of clever people have tried and failed. There's another caveat to this task being difficult for classical computers. If you use Shor's algorithm to factorize 21, then no one's really going to take your claim seriously that you've achieved quantum supremacy. And therefore, your problems should be kind of a scale that, at least now or in the near term, no classical computer will be able to solve. And if you look on this diagram here, you can see that, well, once you're in that regime, a small increase in problem size, so on the x-axis, that should lead to quite a big jump in the classical resources required to solve the problem. Whereas what you hope is that your quantum resources are scaling much nicer, and therefore, if you have this nice quantum computer, it's no problem to kind of crank up the nodule a bit in order to prevent any classical computer in the near future being able to solve the task that you've just solved. So let's talk a bit about performing this task with a quantum computer. So we'll continue with Shor's algorithm. So apparently, I had a look online, the kind of gold standard of breaking factorization classically, so without using any kind of weaknesses or exploits in the factors themselves, is 829 bits. So I've just gathered some of the kind of estimates in the literature here for what it would take for a quantum computer to break a 1024-bit factorization. I appreciate that this is a much larger number, but you can see that all these estimates are in the realms of kind of 10 million qubits. And these are all making assumptions about not just the fact that you can have this many qubits, but also that you can error correct them, that you can kind of control them with your control electronics. I mean, this is like a seriously big number. This is a really, difficult task, right? So Shor's algorithm as a kind of quantum supremacy demonstration is still out of our reach. So before we move on to an alternative suggestion, let's just look at that final step, which is proving that you perform the task. And the ideal way to kind of show that you've performed Shor's algorithm is that someone just gives you the product of some prime factors, you run your algorithm, and you give them back the factors. And then the referee is happy, they say, yes, well, I'm the one who multiplied these, I can verify it, you didn't cheat. So we would like to have some kind of referee who sets the problem for us, and then we give them the solution, which they can then verify. So let's move on to Google's kind of experiment, which was really the first kind of serious claim of quantum supremacy. And they said, okay, Shor's algorithm out of reach, what's an easier task? And they came up with this following experiment. So this is a circuit diagram. So each of these lines corresponds to a physical qubit, and the kind of sequence of operations is going from left to right. And effectively what you do is you choose a set of 1 and 2 qubit unitaries called gates at random according to some distribution. It's not important which one, but you have to choose like the correct ones. And you basically apply them. And once you've done enough cycles of this, you measure all your qubits and end up with a bit string. And so the kind of idealized task in this random circuit sampling is to produce these bit strings X according to the probability distribution. Okay, my syntax has gone a bit funny here, but basically this is just the Born rule. And yeah, basically you choose your circuits at random and you produce bit strings. So is this task difficult? And actually the answer is yes. And not just because we believe that quantum computers cannot be simulated by classical computers, but actually it's based on another very strong belief in quantum complexity, in classical complexity theory, which is called the collapse of the polynomial hierarchy. I'll talk you through that in a minute. But the point is that this is almost strongly as believed as P is not equal NP. It's sometimes called like a silver standard of complexity theory. And there is a small caveat, which is this is a worst case complexity theory belief. So it just says that if you had a classical algorithm which could do every circuit, then this hierarchy would collapse. But we're interested in a probability distribution of circuits. And so we're going to have to strengthen this assumption to say that the average case circuit should be as hard as the worst case. So what is this polynomial hierarchy? So let's talk about the first level. So P and NP are our two sets of problems. And we have our set P, which is all the problems that you can solve in polynomial time. Whereas NP, the problems are a bit harder. You might not be able to solve them in polynomial time. But if I give you a potential solution, you're able to verify whether that is or is not a solution in polynomial time. And you can see the kind of believed relationship between the two of them up in the top right. So that's level 1 of the hierarchy. Probably most of you are familiar with that. So let's move to level 2. And you can see we've kind of upgraded our computers. And we've given each one an oracle. And this oracle is kind of a magic device that can instantaneously solve any NP problem. And so we can ask the same question again. So now with this kind of souped up computer, what are the problems we can solve in polynomial time? And what are the problems which you can verify and answer in polynomial time, given that you now have this extra oracle? And we believe that this is somehow a strictly more powerful computer. So with access to this oracle, you can now verify a whole new range of solutions that weren't possible before. So let's go up again to level 3. And you can see that we've upgraded our oracle now. And unsurprisingly, this new oracle is one that can solve solutions in the complexity class of NP2 instantaneously. And we can ask the same question and get a new set of problems. And you see again, we expect that this gives us access to new problems which we can now verify. And so the polynomial hierarchy belief is that as you upgrade this oracle at every single level, there is a strictly larger set of problems which you can verify the answer for. And if it was possible to classically simulate these circuits, then after this level 3, there would be no new problems. And this is something kind of complexity theorists highly believe not to be true. So that's kind of the abstract complexity theory which is underlying this experiment. So let's go into actually doing the experiment. And one thing hopefully you can note is that the qubit numbers are no longer in the realm of 10 million, but they're actually very reasonable. I mean, this is the size that we have devices today, which is why they were able to do the experiment in the first place. And actually, the other big factor is the depth. So how long you have to do this circuit for is much shorter than Shor's algorithm. And this is useful because every time you do an operation, there's a chance of you making a mistake, there being an error, which is given by these kind of lightning bolts. And you see that the task as we defined it is actually not really possible because our quantum computer has these mistakes built in. Even if we try and correct the errors, there's still going to be a rate of error which we're never going to be able to get rid of. So we should adjust our problem slightly and say that it's enough if we sample from a probability distribution which is instead having these errors built in. So here you can see that some noise channel has been applied to my unit tree. And it turns out that if our circuits have a property called anti-concentration, which indeed the Google circuits do, then this kind of extra condition, the fact that we're sampling from a distribution close to perfect, doesn't really change the complexity theory very much. Turns out this is still pretty difficult. So what is this anti-concentration property? So you can think of it as the probability is spread evenly throughout all the bit strings, or almost all the bit strings. So the most anti-concentrated distribution is just the uniform distribution, where every probability, every string has an equal probability of being seen. And the kind of interesting distribution here is something called the Porter-Thomas distribution. And it's what happens when you do enough rounds of these 1 and 2 qubit unitaries, such that on average, these unitaries start to look completely random over the whole set of qubits. And this is the formula for the probabilities of bit strings. And you can see that this exponential basically suppresses the large probabilities. So you can think of these anti-concentrated distributions as something which looks kind of random, but there are subtle ups and downs which a good enough computer would be able to distinguish. So let's move on to the third thing we need to do, which is actually proving that we perform the task. So our referee says, okay, give me some samples from this unit tree. And I say, yeah, here you go. Here are my bit strings. Like, what does the referee do with this, right? It's not immediately obvious in comparison to Shor's algorithm. But we can go back to the task that we set, and the referee should check, okay, well, is this from one of these distributions that's hard to sample from? The problem is this is pretty hard to check. In fact, it's as hard as the sampling problem itself, which kind of throws a really big spanner in the works because basically in order to show this quantum supremacy with these random circuits, our referee needs to have a classical computer which is actually better than the quantum computer we've just used. So basically I can't show supremacy because I need my referee to be better than me. And there's not really a solution to this problem. This is really baked into the complexity theory assumption that we had at the beginning, as far as we know. There's also another kind of practical issue with this, which is that, well, our distribution looks almost exactly like the uniform random distribution, which is really easy to sample from, right? I just roll a 2 to the n-sided dice, and I give you the bit string back. And so in order to actually even give the referee enough samples for him to check this, we need an exponential number of these. And so we've kind of said, well, our quantum computer can do something efficient, but then we have to do an exponential number of samples, which is not efficient, in order to prove that we've done it. So let's look about how Google got around this problem. So the first thing they did is they said, okay, well, scrap the one norm distance, right? Exponential number of samples, we can't do that. Let's take something else instead. So this is the linear cross entropy, and basically it's a quantity which is derived from the KL divergence, and effectively it takes the expectation value over your noisy circuit of the ideal probabilities. And what is kind of good about this is actually this is a quantity which you can estimate using only a polynomial number of samples from the computer. So we've already solved issue 2 by changing to this new quantity. What about issue 1? Well, Google's solution was not to calculate issue 1, which is a reasonable thing, right? So what they argued is they said, well, let's take circuits which look a lot like the difficult circuits, but have some kind of tweaks to them to make them easy to calculate these probabilities. And then let's calculate the cross-entropy benchmark for these circuits, and then make arguments about our hardware to show that the noise model for these easy circuits and these hard ones should be the same and lead to the same cross-entropy value. So it's up to you to believe how strong evidence that is of supremacy. But even going back to kind of the more rigorous definition, well, by changing our quantity that measures how close our noisy experiment was to the ideal, we've changed our task. And therefore, we've changed the complexity theory which is underlying the task we're doing. So let's take a closer look at this linear cross-entropy benchmark. And there are kind of two important values on the axis. The first is 0. This is the value you would expect to get if you just guessed completely at random. Then there's 1. And this would be the case where you actually perfectly sampled from your circuits, so with no noise at all. And this is only true because we have this Porter-Thomas distribution. It's kind of lurking in the background, so this anti-concentration. But actually, there's a whole scale above 1, which is, you can see that in this expectation, if I have some knowledge about which values of P in the ideal case are more likely than others, well, I could just give you those bit strings. And I can actually push this value above 1. And this is like called spoofing. And in the Google paper, they said, well, we believe that actually everything above very, very close to 0 is hard to do. That's the complexity theory assumption they make. And that's good for them because their values are pretty small. So it's good they've made an assumption that says that their thing is hard to do. But the problem is this conjecture is not true, at least in general. So since 2019, complexity theories have been working on this, trying to analyze it. And there are cases where indeed this spoofing, so trying to guess which are the larger probabilities, you can do with some success. So that's the status of Google's experiment. Let's go back to that little red thing I had in the corner, which is, well, can this random circumsampling be useful for anything? So you should ask, well, what is a natural application of sampling from interesting probability distributions? And there's one answer, but at least I would think of, which is called generative machine learning. So what is generative machine learning? I think it's best understood when compared to discriminative machine learning. So in discriminative machine learning, you have some data, here a picture of a cat, and you train your model to provide the correct label. So it correctly learns, okay, this is a cat. In generative machine learning, you effectively do the reverse. You say, well, here's a label. Can you generate me a realistic looking data point which matches that label? So you can see here the conditions are now reversed. And indeed, we want to sample from some probability distribution which is over the data space. So when talking about generative machine learning, there's this concept of generalization. So you have kind of some true fundamental underlying distribution on your data, you know, all the images of cats out there in the world, and you're only going to give your model a subset of these, which is kind of the training data that your model sees. And you can imagine that you have a model which indeed you can train, you can update the parameters, your loss function goes down, but actually when you go to sample from it, this new data distribution doesn't really reflect the underlying distribution out there in the world. Whereas a good generative model is one that trains on this data set, but actually reflects well what the true underlying distribution is. And this is not really a concept that is in the abstract kind of theory, but it's something that we all saw maybe like 10 years ago or so, and we all saw with pictures of cats. Because they introduced this model called the convolutional neural network, which had built into the structure kind of the underlying rules that pictures usually follow. And so when they started using these models, we saw that the quality of generated images increased 100-fold, all because the fundamental structure of the model reflected well the underlying data distribution. So the million-dollar question, which I'm not going to answer, because I don't know the answer, is, well, okay, so what data distributions do quantum generative models generalize well to? And like this, in some sense, is what everyone would like to know, because we need to know this in order to work out what these models could be useful for. So, you know, what could we hope to see if we had a good quantum generative model? So the first option would be that it just simply fits the data better, right? It's just simply a better model for this underlying data distribution. Maybe that's too optimistic. And so you could say, well, maybe I have a quantum model, which in terms of the fit is roughly as good as a classical model, but it kind of captures a different area of the data distribution. And so when I use it to generate new data points, I kind of see things that classical models are not giving me. Again, this may be too optimistic. We don't know. But you can imagine how in a field like drug discovery, this second option could be very interesting, because being given access to new molecules, well, then you can go in the lab and test their properties, and it could be very valuable. So what is a quantum generative model? Maybe I should talk about that. Well, in a nutshell, it's just some circuit which has parameters in it, and these parameters you can train. And you can train them using a particular loss function, which effectively measures the similarity between the distribution you're currently outputting and the one you would like to output, using this so-called kernel, which is some measure of similarity between the data sets. And what's quite nice is that there are these parameter shift rules which tell you that given a particularly nice structure of circuit and a particular loss function, you can actually train this using gradient descent. And in fact, you can calculate these gradients just by evaluating the loss function at different parameters in the circuit. So you shift one of your knobs to the left, shift it to the right, and this gives you an estimate of your gradient. So that's kind of the general idea of quantum generative models. Let me now connect it to random circuits. So I'd like to introduce you to another random family of circuits. This is not the one that Google used, but it's actually kind of one of the front runners that was used to propose these quantum supremacy sampling experiments. And these are these IQP circuits, which consist of a layer of Hadamards, then a set of commuting diagonal gates, so Pauli Z and ZZ rotations, and then finally another layer of Hadamards. And these have quite a nice structure. They're quite amenable to analysis. And indeed, they share kind of the same fundamental properties as the Google circuits. So the same underlying complexity theory, anti-concentration. And for the kind of proposed experiments, you take these angles to be multiples of, 2 pi I over 8. Pi has somehow disappeared. So how could you make this trainable? Well, you can just replace all these angles by continuous variables. And now, just like the example I had before, I have a parameterized model, and I can calculate the gradients. Of course, in terms of complexity theory, this is a massive change, right? I've completely changed the underlying distribution. I've come up with a new average case complexity. But, it's still an assumption, so maybe we just leave it and wait for someone to try and disprove us. So why have I introduced this kind of new family, these IQP circuits? Well, there's a good reason for this, which is that if you take the loss function and you kind of choose a particular kernel, which is quite a good kernel, I would say, then you can rewrite this as a sum of kind of expectation values. And in particular, these are expectation values kind of with relatively low locality. And this is good because for IQP circuits, it turns out that you can calculate these expectation values just using a classical computer. So that means that when we're doing our training, not just the loss function, but also all of our gradient evaluations, we can evaluate classically as well. That means that rather than using a quantum computer to evaluate every single gradient step, which is slow, which is expensive, you can take advantage of classical computation, you can take advantage of parallelization, the fact that you have no noise in your classical computation is kind of a very practical advantage. And this does not affect the underlying complexity theory, because remember, we didn't say expectation values should be hard. We just said that sampling from the circuit should be hard. So we can train our model classically, but when we go to generate new data points, we still need the quantum computer for that part. Okay, so what's the problem? Why can't we just do this, get some amazing results? Well, the problem is this anti-concentration. So if you want to train a machine learning model efficiently, the number of training data should somehow be polynomial in the size of your model. Because any exponential data set, well, will take an exponential number of time just to read the data set into the machine. So what that means is, if you think about our data set spread out over all these 2 to the n bit strings, well, only a polynomial number of them is going to be non-zero, so it's going to look pretty peaked in this large exponential space. But actually, what we saw is that for our complexity theory assumptions, we needed this anti-concentration property, where pretty much every single one of our bit strings has a roughly equal probability. And okay, you may want generalization, but if you're not even able to approximate the training data, how good a learning model is this actually? So this is kind of the problem that we're currently working on at IQM. And I'll just give you an idea of one of the possible solutions. So here you can see that we have the IQP circuit as before. And we've basically just stuck on the end another trainable circuit. And the purpose of this second circuit is effectively to just peak the distribution. So the idea is that the first half of our circuit gives us something which is hard to do, and then the second half gives us something which is actually useful at the end. The question is this possible? And this balancing act is kind of what we're trying to solve right now. So I've actually come to the end of my talk, a little earlier perhaps than planned. But I just wanted to kind of give you the takeaways that quantum supremacy is something that you should be very skeptical of when someone says they've done. Because, I mean, Google knew about all these issues, and they have all these caveats in their papers, right? They're not claiming something sort of deliberately false. Maybe they overestimated the classical resources required to sample those circuits because, of course, once they put their circuits out there, a bunch of clever people came up with new sampling algorithms for classical computers. But actually, there's a lot of debate and a lot of kind of complexity theory which is going into this question of, can we show a quantum computer can do something a classical computer cannot? And kind of the big issue is that a lot of these proof results rely on this anti-concentration property. So really, we want to move away from this anti-concentration as a proof of difficulty, both in terms of these resources that the referee requires to verify the task, but also for the next step, when we try and apply it to something practical. And like I say, the million-dollar question is really, if you have a quantum model, what kind of data sets does it generalize to? Because it might be that it just doesn't, right? It might be that all the data sets we see in real life don't really follow the underlying structure that a quantum circuit has. So these are kind of the open questions. These are kind of the challenges that I am throwing out there. And then I just want to finish off with like a small plug. So if you're interested in running something on a superconducting quantum computer, you can sign up to IQM's cloud service. They have a free tier where every month you get a small amount of computation for free. So for master's projects, something like that, I highly recommend it. And also, there's open positions always on our website, which I highly recommend you to take a look. So with that, I'm going to end my talk and open up the floor to questions. Thanks.